Alright, so we're picking up with section 1.3, and it's actually taking and talking more about functions and their graphs. It's a continuation of all the things we talked about in section 1.2, and we want to continue with that and go a little deeper. Alright, starting off with a very easy concept, a function that's increasing, decreasing, or constant. So the function is increasing on an open interval I if f of x sub 1 is less than f of x sub 2 whenever x sub 1 is less than x sub 2 for any x1 and x2 in the interval. All this is saying is if we have an x1 that's going to be less than x2, in other words x2 is bigger than x1, then f of x1, f of the lower x value, must be less than f of the upper x value. All this says is that your y values are going to increase as you move left to right. That's all this says. Don't make it more complicated. Now, of course, the math speak here with all the function notation and everything makes it more complicated looking, but it's actually not. It just says this y value is going to be less than that y value as long as this value is smaller than that one. That means that the function is going to be increasing. Now, if the function's decreasing, what do we know? Well, it says that the y value at the beginning or earlier in the interval is going to be greater than the y value for an x value later in the interval. And that means the function's decreasing. But that's the mathematical definition of increasing and decreasing. But you just need to know if it's increasing, it means it's going up as the y value is increasing as we go left to right, and if it's decreasing, the y value is going down as we go left to right. And a function is constant on an open interval I if f of x sub 1 equals f of x sub 2 for any x2 and x1 and y and x1 and y, x1 and x2 in the interval. I think finally got it out. And that means for any x1 and x2. If you just have the two endpoints that are equal, that does not mean it's a constant function if the thing goes up and comes back down. This says that no matter what x value you choose in this interval, the y values are going to be the same. So that's the difference between one that has equal endpoints and one that's actually constant. It doesn't matter what x value we choose in this interval I, the function is going to have a value that is exactly the same for all those values of x. That's a constant function. All right, so on these, let's identify the intervals which each given function is increasing, decreasing, or constant. So we'll do increasing, decreasing, and constant. And we'll just do this in interval notation, remembering that parentheses do not include the endpoints, brackets do. When you're transitioning from a decreasing to an increasing, you typically just leave that open because it's neither one at the endpoints. So for instance, if I'm looking at this function right here for a, it's decreasing over the interval from negative infinity. As far as I know, it goes up, 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 up. So negative infinity down all the way up to 0. And also it's decreasing on the interval from 2 to infinity. Now, remember when you're doing intervals here, you're always doing x values. The intervals that you're identifying are going to be identified using the x values. All right, and where is this thing? Well, crap, I did that wrong. That's decreasing, sorry. So let's change those. And it's increasing over the interval from 0 to 2. And that's the only interval over this thing, over the domain of this function where it's increasing. Now, is there any interval in here where it's constant? No, there's not. So there's none. All right, and when we look over here, we got increasing, decreasing, and constant. And for those of you that are trying to laugh at this, I don't care. Well, anyway, you should care. So anyway, where is this thing increasing? Well, it's increasing from 0 to infinity. And remember, we're talking about and identifying x values. So 0 to infinity. Is it decreasing anywhere? Well, no, it's not. And then so none for that. And where is it constant? Well, it's constant from negative infinity all the way up to 0. Now, this is one of those few places where it's not actually transitioning, but what do we know? We're going to include that endpoint. So it should get a bracket there. Very seldom are you going to end up using a bracket on these intervals when you're talking about increasing and decreasing, but if you do, it's going to be where you've got transitions like this, where you've got breaks in it. It's going to be a piecewise function. You've got a closed dot here and an open dot somewhere else. All right, so you guys try this one. I want you to try it and see what you come up with. And what I'm going to do is I want you to pause the video where you can see this picture and state the intervals, and then start the video back and I'll show you the answer and you can check your work. And I'm going to show you the answers in 3, 2, 1. All right, so here's the answers. It's increasing of the interval from negative infinity to negative 1, so along this. And unioned with, and remember with union, that just means we're throwing the two intervals together to include all the parts where this actually occurs. And guys, if you don't write the little union symbol in there, I'm not going to count it wrong as long as your intervals are correct. But technically speaking, it should have that U in there to show that it's a union of this set and that set. Now the other part is from 1 to infinity, so that means from here going off to the rest of this, the y value is going to go up. All right, it's going to decrease only between negative 1 and 1, so from here to there, and it's a little bit down in the middle, and it's never going to be constant. Now for constant, remember all the values in that interval must be the same. There are places where it stops increasing and starts decreasing, or stops decreasing and starts increasing, but it doesn't stay constant there. That's just a maximum value and a minimum value. So it's not going to be constant at those places. All right, and speaking of maximums and minimums, we have relative maxima and relative minima. These are the points at which the function changes its increasing and decreasing behavior, and they are used to find relative maximum and relative minimum values. Now I just said that it's the places where it changes. It's not always. Let me change that right now. It's not always where it changes its increasing and decreasing behavior. Sometimes it doesn't end up being that way. Now, here's the definitions of relative maximum and relative minimum values. Now, when we say relative, the reason we say relative is it's relative to those points around it. It's not going to be the absolute highest point. It's not necessarily going to be the absolute lowest point. It might be, but it's not guaranteed to be. Relative just simply means that it is the maximum value for those points around it, or the minimum value for those points around it. Okay, so a function value f of a is a relative maximum of f if there exists an open interval containing a such that f of a is greater than f of x for all x that does not equal a in the open interval. Now remember what we're talking about when we're talking about an open interval. Let me change colors here. And an open interval is an interval where we have open dots on each end. There is an open interval. Let me go ahead and mark this in so you can actually see it a little better. So let's say we're looking at that open interval right there. If we had a right there, that is going to be a relative maximum. Relative maximum, local maximum, they're two different ways of saying the exact same thing. Local is also another way you say that. Now, let's follow through the definition here. So we have f of a, that's right there. And what do we know about every other x value in this thing? Well, it's going to give us an f of x that's going to be what? Less than that value of f of a. It is the highest value, the highest y value right there. Any other x value in this open interval is going to be smaller. That is why that's a relative maximum. And the same exact idea for the relative minimum. F of b must be less than f of x for all x not equaling b in the open interval. So whatever interval we're talking about here, every single point other than f of b is going to have other than b is going to have a larger y value to go along with it. That's why this is a relative minimum. All right, definitions of even and odd functions. This is something that you're going to need to remember. We've done them before. You've done them in Algebra 1, you did them in Algebra 2, now we're doing them again in Pre-Cal, but this is something that you're going to actually transition over into some of the other functions. We've only looked at them as far as polynomials are concerned, but we're actually going to look at them later in the class in terms of trig functions. But anyway, let's start off with the definition. A function f is an even function if f of negative x equals f of x for all x in the domain of f. What that means is if I have a negative value and a positive value of the same number, if I put those numbers in the function, I'm going to get the exact same value. So literally, if it's an even function, it doesn't matter if I find f of negative 4 or f of 4. If it's an even function, these things are equal. Now, how in the world do you know that? Well, it's really easy, and we'll talk about that in just a second, how you prove that. You actually literally will plug in a negative x and see if it's going to be the same thing that you started out with f of x. But we'll talk about that in just a second. All right? The function f is an odd function if f of negative x is equal to negative f of x for all x in the domain of f. Now, similarly to what we did up here, this thing says that if I plug in a negative value, if it's an odd function, I'm going to end up with the negative or the opposite of what I would have gotten had I plugged in the positive number. That's it. So let's say that f of negative 4 equals 7. If it's an odd function, f of 4 would have equal. Let me do this a little different. Well, let me put that negative right there. That means that f of 4 would have been 7. So f of 4 would have been 7, and f of negative 4, we end up just throwing that negative out in front of it right here to make it negative. So that's all an odd function does. All right, so let's identify the even and odd functions. And the way you're going to do this is this. You're going to determine whether or not the thing is even and odd, all by doing the same thing. You're going to go ahead and you're going to plug in that negative x, and if f of x equals x to the third minus 6x, what do I know? Well, I can, if I do f of negative x, that's going to be give me negative x to the third minus 6 times negative x. Well, what's negative x to the third power? Well, negative 1 to the third power is negative. X to the third power is x to the third. Negative 6 times negative x gives me plus 6x. And then you ask yourself, is this the same thing I started off with f of x? Well, obviously, no, it's not. Okay, so then what you want to do is you want to factor out a negative. So if I take a negative out of this term and this term, what do I end up getting? I get x to the third minus 6x. Okay, now what you ask, is this thing in the parentheses the same thing that I started off with? In this case, it is, and we got the negative out front, so what does that mean? That means this is an odd function. Here's my f of x. Here's my negative f of x that I get when I plug in a negative x. Ta-da, easy. All right, let's look at, let me get one of my better colors here. All right, so let's look at g of x and determine if it's even, odd, or neither. So with g of x, I'm going to find g of negative x and evaluate it. So what happens is I put in a negative x here, negative x raised to the fourth power minus 2 times negative x, quantity squared. Remember, just plugging in the negative x everywhere I got an x. Now, what happens when I take a negative and I raise it to an even power? It's going to be a positive. So this becomes a positive x to the fourth. And then over here, negative x squared is going to give me x squared, positive x squared. And if I multiply negative 2 times positive x squared, I'm going to get negative 2x squared. All right, and what do I know? I look right here, I say, is that the same thing that I started off with? And look at there, ding, 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 it is. So if that's the same thing I started off with, if f of negative x equals the original function, what do I know? This is an even function. All right, and then the last one here, we're going to do the same thing. H of negative x equals negative x quantity squared plus negative 2, well, where am I doing that? 2 times negative x, getting ahead of myself there, plus 1. Now, when I simplify this, this is going to be negative x squared raised to the second power. That's just going to give me a positive x squared. Positive 2 times negative x gives me minus 2x. And then plus 1 is not affected by the negative x at all. Now, is this what I started off with? X squared's good, but the middle's not. So it's not. That means it's not going to be even. And then if I factor out a negative, I'm going to have negative x squared plus 2x minus 1, because all my signs are going to change there. And in parentheses, that is not what I've got here. So what do I know? It's not even and it's not odd, so it's going to be neither. All right, you guys try those three, and I'm going to give you the count of 3 again like I did before, and pause it, try those, do what I just did with the ones above, and see if they're even, odd, or neither, and then I will show you the answers to them. All right, so here's your answers. You've got f of x. You do f of negative x, you're going to get the exact same thing. It simplifies down to what it was before. So you end up with so f of x is an even function. With b, it's an odd function because when you end up putting in the negative x and simplifying, you get negative times parentheses 7x cubed minus x. Well, the 7x cubed minus x is the same thing you started off with. So it's an odd function. And then h of x, you end up getting something that was neither what you started off with nor the opposite of what you started off with, so it's neither. Now, guys, let me tell you something real quick. I know a lot of you know a little secret or a shortcut that you just look at the powers, and that's great with polynomials. There's only one problem. It doesn't work for functions that are not polynomials, and we're going to deal with those later. So I really want you to make sure that you know the history, not really the history, but the definition way of finding out whether a function is even or odd. So don't stick with just knowing the power rule thing. with all even powers, it's an even function. All odd powers, it's an odd function. Mixture, it's neither. That's good to know, but you also need to know the definition-wise how to prove it. All right, even functions and y-axis symmetry. Well, if we have a function that's even, it's going to be symmetric with respect to the y-axis. Now, guys, I need you to actually start looking at this in more than one way. Don't just look at this and say, oh, okay, well, f of negative x is equal to f of x. Duh, it's even. I also want you to think about graph. What happens here? Remember, we're saying that these two y values, remember, f of negative x and f of x are just y values. And we're saying what? We're saying we have the exact same y value whether the x is a positive x or its opposite, the negative x value of that. That's telling us what we're looking at on this graph right here. Notice that we have the same y value when we have a negative 2 as we do when we have a positive 2. There's your 2, there's your 2. We have the same y value. There's your 3, there's your negative 3. We have the same y value. That is what even actually means. Make sure that you can visualize that as well. It helps. All right, odd functions have what's called origin symmetry. And the easiest way for me to remember that is that it just reflects across both axes. It's going to reflect across the y-axis, and then it's going to reflect across the x-axis. It has to reflect across both of them. Does not matter what order, but it has to reflect across both of them. So here you could also reflect across the x-axis and then across the y-axis to get right back to the same thing. Now, what do you also notice here? When x changes sign, so does the y. So that's the thing with it. X and y are both going to swap signs to have origin symmetry. So here we had 2, 8. Here we have negative 2, negative 8. All right, now we want to graph this piecewise function. And I know this is there's kind of a lot of things in this section that are kind of spacing all over the place. But piecewise functions are very important because they're actually more realistic than a regular function that we're going to deal with. And the reason why is because piecewise functions are defined by different things at different intervals of your graph. Well, guess what? Life's not defined by one single graph for a group of, for all time. It's going to change as well. And that's why piecewise functions are important. Things are going to change, and when they change, it's going to behave more like a piecewise function. All right, so what a piecewise function is, if you're not familiar with it, it's a function that's simply defined by different equations during different parts of the domain. So for instance, right here, when x is less than or equal to 1, we're defining this function as x plus 2, which is nothing more than a line. Now, when x is greater than 1, we're going to define this function as just simply having the constant value of 4. So when I mark in my 1 here, I can go over and do 1, and then I can go up 1, 2, 3, 4. And I'm going to go up there and I'm going to put an open dot. Now, why do I put an open dot? Well, because x greater than 1 is not equaling when x is equal to 1. So it may fill in with this other part, it may not, but I know that it's an open dot and that's where I'm starting. And then x greater than 1, for all values of x that are greater than 1, I just draw a line that has a value of 4. And that's a horizontal line. Now, for all x values that are less than 1, I'm going to draw the line x plus 2. Well, remember, x plus 2, you can think about it because this is really what it says. Y equals x plus 2. That's in slope-intercept form. What's the y-intercept? 2. What's the slope? 1. So I'm going to go up 1 and over 1. So I've got a point right there. Now, is that point right there going to be included? Well, less than or equal to 1, so yes, it will be. And then all I have to do is connect these dots. You can draw more points if you want to, but that's my piecewise function right there. For all values that are less than or equal to 1, I'm defined by this line. For all values that are greater than 1, I'm defined by this line. All right, I want you guys to try this one. Once again, I'm going to pause the video. I'm going to pause it for mine. I want you to pause the video. I'll give you the countdown, and when I count down, I'll show you the problem. So pause it before I finish the count. I'm going to show you the graph in 3, 2, 1. All right, so here it is. For all x values that are less than or equal to -1, my y value, remember f of x is just another way of saying y, is 3. That's this part right here. And of course it should have an arrow because it's going to continue. And then for all values of x that are greater than -1, it's going to be defined by the linear equation x minus 2. So there's my y-intercept of -2. And it's got a slope of 1. So up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. And I can get a bunch of dots. And once again, that is going to continue on forever too, in that direction. So defined for part of the domain is 3. The rest of the domain as x minus 2. That's all a piecewise function is, guys. When you see this, don't overcomplicate it. Just break it up into parts and graph all the parts individually. Now, the last thing we're going to talk about is the difference quotient of a function. Now, this is going to lead directly into part of the thing that you're going to cover in calculus if you ever take it. But we're just going to deal with the difference quotient as it is right now. The expression f of x plus h minus f of x all over h for h not equaling 0 is called the difference quotient of the function f. Now, don't overcomplicate this. What is f of x plus h? It's just whatever function we're dealing with, and in place of x, we're putting x plus h all the way through the thing. So, if f of x equals 2x squared minus x plus 3, find and simplify each expression. So first things first, let's find f of x plus h. So f of x plus h is equal to 2 times x plus h squared, that's taking the place of this x, minus x plus h, put that in parentheses, taking the place of this x. The reason in parentheses is I'm subtracting the whole thing. We need to subtract x and subtract h. If you leave those parentheses off, guess what you're going to do? You're going to end up adding h and you're going to get the wrong answer. And then plus 3. Now, you've got to FOIL this out. Don't just square the x and square the h. That's not right. You're going to have 2x squared plus 2xh plus h squared minus x minus h plus 3. I want to distribute the 2 through. I'm going to have 2x squared plus 4xh plus 2h squared minus x minus h plus 3. Alright, so there is my f of x plus h. And then all I want to do now is I want to put it over here into this thing. So let me change colors here just so we don't get it confused. There was part A, just the f of x plus h. And then now I'm going to move over here, I'm going to do the whole thing. So this whole thing right here is going in place of this, because I've already found it. So you got 2x squared plus 4xh plus 2h squared minus x minus h plus 3. And then I'm subtracting f of x. So subtracting, what was f of x? 2x squared minus x plus 3. And that's all over h. All right, so now we're going to simplify here. Some things should cancel out. I'm going to be honest with you guys. If you've done everything right, everything on top that does not have an h should cancel out. I've got 2x squared there. I've got a minus 2x squared there. And I didn't distribute. Do you guys see my error? I'm subtracting the whole function, and I forgot my parentheses. See how that works? See how that messes you up? So when I distribute that through, it will be negative 2x squared plus x minus 3. All right, so now my negative x and my plus x are going to cancel each other out. And my 3 and my negative 3 right there are going to cancel each other out. So the only thing that's left is going to be what? 4xh plus 2h squared minus h, and the rest of that canceled out, all over h. Now this is why you know that you've done something wrong if you end up with something up here that doesn't have an h in it. Notice here I've got a common h all the way through. I'm going to actually factor that thing out. So I'll take out my h from here, here, and here, and that's going to give me 4x plus 2h minus 1. Don't forget that minus 1. H divided by 8, negative h divided by h is going to give you a negative 1. That's where that minus comes from. And then divided by h. And the whole reason that you're looking for that thing to factor out is so it'll cancel out with the h on the bottom. So now you have 4x plus 2h minus 1. And that is simplified as much as possible. Now, in calculus, you're going to take one more step, and you'll take the limit as this h value goes to 0. Well, what happens if this number right here is 0? You just end up with 4x minus 1. Well, guess what you just did? You just did calculus. That's called a derivative. Ta-da! All right, you guys try this one. I'm going to pause it again. You need to pause it again. Try the problem and then come back and check your work. I'm going to show you the answer in 3, 2, 1. Okay, so there's the answer. You can pause it if you need to go back and look at this and see where the work is. But you simplify down. That's not really simplified because there's no simplification. You just did it and expanded it out. And then here, of course, you're going to cancel out everything that does not have an h in it, or it should. Now, guys, that's a way to check your work. Don't just go through and cancel out everything. Make sure that you've got the right signs for that to cancel out. Otherwise, you may have mistakes elsewhere, too. So when we do, we get negative 4xh minus 2h squared plus h. We've got a common factor of h there that we can cancel out, factor out, and then cancel with what's on the bottom, and that leaves you with negative 4x minus 2h plus 1. So that is your difference quotient there. All right, that's it. See you soon.